Alrighty, everybody, welcome to chapter 13. These are the electrons in the atom. Yes, we go from chapter 5 to chapter 13 um, because, well, actually, we do chapter 5 to chapter 28 to chapter 13 because this is where we talk about the atom, then we talk about the nuclear, and then we talk about our electrons. Textbooks aren't always written in the ways that make most sense for students. But what is important is that we take a little pretest. Yes, I know that you've done this for other chapters, but I want you to review the evolution of the atomic model, which we did in chapter 5. You should recognize Democritus, Dalton, Thomson, and Rutherford's names. So take out a piece of paper and write each of their four names in and draw what they thought the atom looked like. This is in chronological order, so this is the earliest, and this is the latest that we have gone over in our work, but you're definitely going to see that we evolve from there. Okay, so that's what we're going to do for this first section. We're going to review over our famous scientists that we have seen before. So first we saw Democritus. He's the one that was in the year 342 AD, and he said that all atoms are made up of indivisible particles. The atomos, and I told you how we like slice stuff in half a bunch of times from the previous videos, so you can definitely check those out. Then there's the father of chemistry, John Dalton, right here. He came up with this indestructible mass. There's no subatomic particles, but he was quickly disproven with J.J.Thomson's cathode ray tube experiments because he came up with the plum-pudding model. I call it the mint chocolate chip ice cream model because mint chocolate chip ice cream is so good. But it is this collection of randomly scattered electrons through positively charged material. There is no nucleus yet in this timeline. There are no protons, no neutrons. So just this random scattering of plums, just like these randomly scattered electrons that are all throughout our positive material, which would be like the pudding or the ice cream or the rest of the atom here. And he's the one that said that those electrons are just in that lump of our positively charged material. Okay, then we have our Ernest Rutherford, who did the gold foil experiment and said that the alpha particles that are positively charged, the helium nuclei that are shot at the gold foil, most went straight through, but every once in a while we saw a deflected particle that was picked up with a fluorescent screen. So there had to be this nucleus where we saw it positively charged and it was really, really dense. So that's where we came up with that model since then. Okay, so that gold foil experiment, basically these alpha particles, which are positively charged, deflected off of the positively charged nucleus because two like things repel one another. All right, so that is a little review of what we did in chapter 5. So this brings us to the new slides, which is with Niels Bohr. And Bohr was actually Einstein's lab assistant. And what he did is he figured out that there is some pattern to the way that the electrons travel. Okay, and this is probably the most common example for our atoms and the arrangement of our electrons. I'm sure you have seen pictures like this before. This pathway, this orbital, is going to show that there is a distinction between the different layers of our atoms and the way that these electrons are arranged. So He actually came up with energy levels, which is really quite amazing. And it worked for the hydrogen spectra that he looked at. Now, hydrogen is number one on the periodic table, so it has one electron. All this stuff worked out for hydrogen, but unfortunately not for others. So when he looked at his hydrogen spectra, he saw the nucleus was here, and then there was a first energy level, and second energy level, and third, and fourth. So basically, it was like lanes of a track. All right. And for those of you that have ever run on a track, which I'm sure most of you have, if this is the start or end line, finish line, if you start right here and you do one full lap, that's going to be a certain distance, okay? In track, it's usually going to be 400 yards here. It'd be meters in other places. The person in lane 2, when you stay in your lane, all right, when you stay in your lane, they don't really start right here. They actually start right here because this length would be 400 meters. And the person in lane 3 would start up here. And the person in lane 4 would start all the way up here. So you have this staggered start in order to keep things even, because this is going to take the lowest amount of energy and this is going to take the highest amount of energy. So it's always very interesting to see how this stuff applies to our everyday lives, because the lowest amount of energy is going to be closest towards the infield of your track, and then the highest energy would be out here. If the person out here in lane 4 or on our typical track out in lane 8 started here, they would be running more than 400 yards. Okay, so you have to be very careful about that. All right, so the final model of the atom is going to be what we use today, and that is referred to as the quantum mechanical model, the QMM for short. The quantum mechanical model is widely accepted as being the current model of the atom and how electrons are arranged. And the way that the quantum mechanical model differs from the planetary model that Bohr said it was just going to be these lanes is that the quantum mechanical model describes the probability of finding an electron in space around the nucleus. Okay, and it's not just going to be circles. It's not going to be spheres. All right, it's based off of the equation developed by Edwin Schrodinger, which, if you know anything about him and his cats, and a little bit with Heisenberg's uncertainty principle, where things can possibly be and possibly not be, a little bit from Einstein. Like, all these scientists actually kind of worked together and off of one another, basically to disprove one another and really come up with accurate representations. So it describes the probability of electrons being in orbitals. So these orbitals are s, p, d, and f orbitals, which we'll go over in the next video. The s orbitals are spherical in shape, p orbitals are dumbbell in shape, d orbitals are double dumbbell in shape, and f orbitals are just crazy complex with these three-dimensional regions of space which are really complicated. So it's not just going to be a nucleus in the center with just some things around it. It's going to be a nucleus in the center with a variety of shapes and things around it. And you can kind of think of it as a lightning bug that is stuck inside a jar, and that lightning bug can go anywhere inside the jar. That's what it's like to be an electron inside an orbital. It can go anywhere inside of it. All right, so in the next video, we'll take a look at the s, p, and d and f orbitals, and then we'll talk about electron configurations.